Welcome back, Joni. Glad to see you here for the final day of learning about chemistry. After today, you will have caught up to your class and everything that you missed, and you will be ready for the test next week. So the last topic that you missed while you were asleep in class was on acids and bases. So acids and bases are quite interesting, actually, and you may have learned some basic things about them in the past, so I'll just quickly review them. So what you are likely familiar with is the Arrhenius theory, which is that acids release H plus in water, and then you can see by the example equation there, hydrochloric acid is hydrogen ions and chlorine ions, and then a base releases hydroxide, or OH minus in water, and then you can see the example equation. Sodium hydroxide becomes sodium ions and hydroxide ions. But it's important to note that even though we see H plus written, it is actually H3O plus, which is hydronium, and that's a result of water combining with the hydrogen ion to become H3O plus. So that's what an acid is. You can simply continue writing it down as H plus. It's usually referred to as H plus, but it actually does mean hydronium, which is H3O plus. Now, it was discovered many years ago that things could be acidic or basic beyond just this definition. So sometimes some acids maybe wouldn't release that. So they needed to figure out a definition that expanded upon this original idea. And two men, the last name's Bronsted and one is Lowry, hence why this theory is called the Bronsted-Lowry theory. They discovered that an acid is a proton donator, which is H plus, and the reason why it's referred to as H plus is because when you have an H plus ion, hydrogen, the atomic mass is 1. All it has is a hydrogen. All that's in a hydrogen is a proton, right? There's no neutrons in it whatsoever. So, and it's also lost the electron with a charge of plus, so that's why it's a proton donator. And bases are a proton acceptor, so they gain an H plus ion. And these must come in pairs, of course, because where would the acid donate it then? And a substance that can be both an acid and a base in certain situations can be referred to as amphiprotic. Now, before we get further, I have a very, very funny joke that I came across the other day as I was teaching the class. Okay, behold. Why would the military use acid? Get this. To neutralize the enemy base. Now, if you don't get it, it's in the Arrhenius theory, when an acid and a base react, it neutralizes one another, and it becomes a salt in a water. So it's quite funny how they would use acid to neutralize the enemy base. So I thought that was pretty funny. So I wanted to incorporate that into there. Anyways, back to the lesson. So this new theory kind of covered significantly more acids and bases. Now compounds, I should say, such as hydrofluoric acid could now be included in this theory when before it wasn't an Arrhenius acid. However, there's actually a third definition, and this is a Lewis acid or a Lewis base, which is actually referring to electron donation and gaining, but that is usually covered in university. In this lesson, we're only going to be going over Bronsted-Lowry. So it's important to note that there are strong acids, weak acids, strong bases, and weak bases. What I just mentioned earlier, hydrofluoric acid, is an example of a weak acid. The Arrhenius theory only referred to strong acids and strong bases. But the Bronsted-Lowry theory incorporates weak acids and weak bases into it. So a strong acid before was an acid that 100% dissociated in water. Essentially, an acid that, when reacts with water, one completely becomes hydronium. A weak acid only partially dissociates in water, so it's anything less than 100%, even if it was 99.9%. It only partially dissociates into water. So, for example, hydrofluoric acid reacts with water to become hydronium and fluorine ions. But it doesn't 100% do this, maybe 99%, and so it becomes an equilibrium, just because of the fact that it's not 100%. And if you remember, when I was talking about chemical equilibrium the other day, a few reactions are actually in non-equilibrium because it's rare that 100% reactants becomes 100% products. So this is an example of weak acid, and then base is the same thing, or just with hydroxide instead. And yeah, so this is represented by these arrows, which is equilibrium. Now, before we get into example problems, I just want to introduce the pH scale to you. So the pH scale, I am very certain you've heard of this before. It's a scale that measures the acidity, or I wonder what the term for base acidity is. I don't know what basic. Yeah. Basic, that's funny. I was just, acidity, base acidity, kind of lost the term there. But yeah, how basic or acidic a compound is. And some key things to know. So anything with a pH less than 7 is considered acidic. Anything with a pH greater than 7 is considered basic. And anything with a pH of 7 is considered neutral. Water is an example of a pH equaling 7. Interesting side note, actually, the vast majority of food and drink that we consume, the vast majority, not all of it, is actually acidic. Even things that you wouldn't expect. There are very, very few basic food items that we actually consume. Even if it's only slightly acidic, most of the food items we consume are indeed acidic. Basic substances include oven cleaners, or really any cleaning things, but also can be used in cooking, like baking soda or baking powder. Ammonia is another example. Examples of acidics, basically just foods we have, or drinks, like soda, very acidic, as well as something like stomach acid, of course. And yeah, neutral water is an example. Although water that's being polluted becomes acidic, of course, so I'll just say that. Okay, so a difference in pH, so if you go up 1 on the pH scale, it becomes 10 times more acidic. If you go down 1 on the pH scale, it becomes 10 times more basic. So a change of 1 in the pH scale is a 10-fold difference in concentration, and that has to do with logarithms, of course. And this leads to some key formulas that you can see here. To figure out the pH of a substance, you simply take the negative log, which can be referred to as anti-log, of the concentration of hydronium of that substance. The concentration of hydronium you can figure out by putting 10 to the power of the negative pH. pOH simply refers to the other side of the pH scale. So typically pH of 1 is extremely acidic. That can also be referred to as a pOH of 13. So pH and pOH are just simply opposites of each other, reciprocals. So if you're referring to pOH or pH, pOH is the exact same thing. And then I actually could have rewritten this as pH plus pOH equals 14, because the pH scale goes up to 14. And then a quick side note, this is basically the equilibrium constant of water at 25 degrees Celsius, 1 times 10 to the power of 14. 14 because there's 14 numbers for the pH scale. Okay, so using these formulas, let's calculate the concentration of hydronium and the concentration of hydroxide for 0.20 molarity hydrochloric acid. Hydrochloric acid, actually, I will show you this real quickly. Here is a list of the relative strength of Bronsted-Lowry acids and bases. These 6 top reactions are strong acids, and the bottom 2 reactions are strong bases. Everything in between is the weak acids and bases. So as you can see, the Arrhenius theory only covered the strong ones, so really only these ones and these ones. All these in the middle were not included in Arrhenius theory, but the Bronsted-Lowry theory allowed it to include all these other types of acids and bases. Hydrochloric acid, as you can see, is a strong acid, not a strong base. Let me get that right. So it is a strong acid. One quick thing to note, because strong acids 100% dissociate in water, and remember how I said acids and bases come in pairs? Well, with strong acids, the conjugate, because HCl becomes hydronium and chlorine atoms, the conjugate, which is essentially the opposite of hydrochloric acid, it never acts as a base. In weak acids and bases, like hydrofluoric acid, the fluorine atom, or ion I should say, can act as a base, and the hydrofluoric acid acts as an acid. But with strong acids and bases, the conjugate of a strong acid or a strong base never acts as the opposite. That might be a little bit confusing. I'll definitely clarify that as we work through later examples. But yeah, let's start with the first example. So let's use the formula. H3O plus equals 10 to the power of negative pH. How can we figure this out? Actually, I may have actually forgot to include a formula. Actually, yeah, I did. Kw, here's one other formula I forgot to include. Kw equals H3O plus multiplied by OH minus. So the concentration of hydronium times the concentration of hydroxide equals Kw. Okay. Now we can perform this equation, or this question. Okay, let's begin. So since this is a strong acid, we know that HCl, which is 0.20 m, will become H3O plus, but will also be 0.20 m. With a weak acid, this might be anything less than 0.20 m. With a strong acid, it fully dissociates, so of course this will also be 0.20 m. With weak acids and bases, you have to use different types of calculations, but this is dealing with a strong acid. Okay, so because this is a strong acid with a pH of 1, the concentration of hydronium will actually just be 0.20 m. Right, as you can see here, it becomes 0.20 m, so that's actually the answer for H3O plus. So H3O plus equals 0.20 m, and that's one answer. One answer right there. Okay, so knowing that, there's actually a few different approaches you can take to this, but what I like to use is this last formula, where you can simply use this equation, plug those in. So we know that essentially 1.0 times 10 to the power of 14 equals, what does that equal? 0.20 times the concentration of OH. That's essentially what we're at for this question. How can we do this? Well, we can rearrange this to become, let's see here. We can rearrange this to become concentration of OH minus equals the Kw over the concentration of hydronium, which would be 1.0 times 10 to the power of 14 all over 0.20, as that's the concentration. Form that into your calculator, and we will get a concentration of hydroxide to be 5.0 times 10 to the negative 14. And that is our concentration of OH minus. right there.